My today's topic is application of finite automata in networking. So let's start. So firstly, what we will discuss in today's topic is first introduction. What is finite automata? Types of finite automata. Benefits of finite automata in networking. Then applications, TCP/IP protocols, routing algorithms, network security, firewalls, intrusion detection systems, DNS, and future trends of finite automata. So let's start. Introduction. Finite automata are mathematical models used to design and analyze network protocols and behaviors, making them fundamental to the functioning of networks. Over the next few slides, we will explore how finite automata impacts networking from protocol design to security. Let's dive into its important topics. What is finite automata? Finite automata is an abstract computing device. It is mathematical model of a system with discrete input-output states and a set of transition from one state to another that occurs on input symbols from the alphabet sigma summation. A finite automata is defined as a 5 tuples. M is equal to Q, comma, summation, comma, delta, comma, Q naught, comma, F, where capital Q symbolizes sets of finite set called states. Summation symbolizes finite sets called alphabets on which the finite automata is made. Delta symbolizes the transitions from one state to another on a particular input or symbol, whereas Q naught is the start state of the transition or the finite automata, and capital F is the final state of it. So let's move ahead. Now, what are the types of finite automata? There are two types of finite automata mainly: deterministic finite automata and non-deterministic finite automata. So what are they? Deterministic finite automata: one unique state transition for each input symbol. What does that mean? Like, let us assume that from Q naught state we have a transition for input symbol A. Then there will be only one transition available from Q naught on input symbol A, that will be, let us assume, Q1. No other transition can be performed from Q naught to any other state on the same symbol A. Whereas in non-deterministic finite automata, multiple possible state transitions can be possible. Like from Q naught for input symbol, I can go to Q naught again, or else for Q naught only on input symbol A, I can go to Q1 also. So this is the major difference between deterministic finite automata and non-deterministic finite automata. Now, transition diagrams. A transition diagram or a state transition diagram is a direct graph which can be constructed as follows. The steps to construct a transition diagrams are: firstly, each state, that is capital Q, is represented by a circle, is represented in a circle. Example, you can see Q1 state. We draw a circle and inside it we write Q1. This is used to represent a state, where from transition from one state to other is represented using an arrow symbol. As you can see that transition from one state to another in the given diagram. And now, how we represent a start symbol? For representing a start symbol, there is an arrow pointing towards a symbol, but that arrow doesn't have any source. This tells us that the symbol, that state, is the start state. And now how we represent final state is, for final state, there is we draw two circles and inside that we write the state. So now, what are the benefits of finite automata in networking? Firstly, efficiency, improving network performances and resource allocation. Secondly, reliability, reducing network failures and improving fault tolerance. And third, security, enhancing network security and threat detections. So now let us start and see the first most TCP IP protocols application. So finite automata, particularly FSMs, finite state machines, are used to model and implement the TCP IP protocols, which governs the data transmissions on internet. These FSMs define the various states and transitions that guide the establishment, management, and termination of connection, ensuring reliable and orderly communication across the vast network of the internet. Now, next is application on routing algorithms. So, finite automatas are employed in routing algorithms to determine the optimal path for the data packets within a network. These routing algorithm utilizes FSMs to represent network topologies and make decisions about packet forwarding. FSMs define the possible routing states and transitions and conditions for selecting the best path, ensuring that data packets are efficient and accurately delivered to their destinations, regardless of the network's complexity. Now, application of network security. Finite automata are essential in network security for tasks like intrusion detection, traffic filtering, and access control. These finite automata models, especially FSMs, are integral to security applications and networks. FSMs are used to define security policies, detect unauthorized access attempts, and filter traffic based on predefined rules. There will be a set of rules on which these FSMs will be designed, and according to that rules, we can use that for network securities. Next is firewalls. Firewall utilizes finite automata, commonly in the form of FSMs, to scrutinize and control network traffic. These FSMs, guided by predefined rules, make real-time decisions permitting or blocking data packets. They serve as the first line of defense in network security, protecting against intruders, unauthorized access, and potential threats by enforcing access policies and filtering traffics. Now, intrusion detection system. Intrusion detection systems employ finite automata, often in the form of finite state machines, again FSMs, to analyze the network traffic pattern and identify suspicious activities. So what we are doing here is we are actually there. We are creating a finite automata based on certain patterns happened in the past, uh, which caused some suspicious activities, and we train that FSMs. So whenever the next traffic pattern, it checks whether the next traffic pattern is somewhat detects that it is similar to somewhat in the past, it will trigger an alert that takes actions to mitigate potential security breaches. In this way, finite automata serves as the guardian of network security, keeping a watchful eye on network activities to ensure early detection and response to threats. Now, next is DNS. Finite automatas are used in DNS for name resolution. DNS employ finite automata to efficiently translate human readable domain names into IP addresses that computer can use to locate the actual address on the server. So Finite Automata help to locate servers on the internet. Finite Automata processes and match the domain name queries and ensuring the correct IP address for a given domain name. This foundational role of Finite Automata in DNS ensures seamless functioning of internet by enabling translation of user-friendly domain names into their actual IP addresses on the internet. Now, what are the future trends of Finite Automata? Finite automatas can be used in AI ML programs or projects in future. Secondly, they can be used for software defined networking, that is SDN, and also for quantum networking. So conclusion, finite automata. So I would like to conclude the video here by finite automata play a vital role in networking, shaping how data flows and networks operate. As we look ahead, their role will only expand with integration of ML, quantum networking, SDN, etc. In an ever evolving landscape, finite automata will continue to secure and enhance the networks that power our digital world. Thank you, everyone.